in the second 2, etc. And here we will try to consider all possible permutations and find the best solution possible in this experiment. And this is basically the result we can see. We're quite successful actually in detecting correct rearrangements, right? We can see that some misclassifications, of course, happened. Like here, we can see that this rearrangement was not present originally, but we identified 10 of them for the fourth component. But it seems like this idea works, more or less. Of course, some disadvantage, like here, you can see that there are many rearrangements that do not even happen to be, like, we do not have any digits corresponding to these representations, right? We don't have any data points corresponding to this representation. So it would be good to just get rid of those representations that are unnecessary. And we can, of course, do something like a search. We can either do it in backward or forward way. So here, if we do it the forward selection, we start basically only with standard arrangements, right? And then we try to add one additional rearrangement at a time. And we continue doing it until we have an improvement in BIC, and you can see adjusted trend index. So it actually changes quite considerably. Oops, once again. Okay, if we do it in the opposite direction, we start with all rearrangements included in the model, and then we start dropping them one at a time, also based on BIC. Actually, here you can see that our adjusted trend index did not change that much, right? There are some minor changes over the course of the algorithm, but it doesn't change that much. So in this particular case, basically our parameterization does not cause any issues if we're interested in just in clustering results. But back to our example. Of course, we have many points, right? 8 data points, and we cannot go for all possible permutations of them, right? But the good thing is that we can make some reasonable assumptions, right? We can assume that people draw zeros this way, or they going this way, or going like clockwise, right? Of course, we can consider as many permutations as needed, but we will assume that there are no people who draw zeros like this. Right? Because it's quite unusual, right? So this is going to be our assumption, and this is basically the styles we can choose as reasonable ones. So you can see that we start with different data, different initial points here, 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 etc. And in the first row we go this way, in the second row we go clockwise, right? So similar story with Aves. Actually, we covered, like, we believe that, like, all reasonable ways to draw Ave. This way, like, you can follow, like, 1, 2, 3, 4, 5, 6, 7, 8. Here is 1, 2, 3, 4, 5, 6, 7, 8. And there should be even more unusual ways, like 1, 2, 3, 4, 5, 6, 7, 8, etc. Right? The different arrangements, but with nines, there are also several of them. Depends on how you draw it, like this way, how big your loop here is. And this is basically the result that we can get if we do forward selection. So this is basically the result if we do not do any selection for representations, and this is if we run the forward selection. So you can actually, so this is the original MIGMM, and this is the one based on the forward selection. And you can actually see that we have an improvement in the adjusted trend index, even though we introduced two representations that are very, very rare, right? But again, it's these additional representations do not really over-parameterize our model because we just need one mixing proportion. This is just one parameter. So BIC is not affected that much by introduction of an additional representation. And you can see also that our BIC improves somewhat. Okay, let's skip this. And this is basically this idea, instead of having just linear transformation that we considered, we can have some more general transformation, some different functions. And this is basically, this will conclude the talk that I planned to finish last time. Okay, so this is just, I thought it was an interesting application of how we can use the EM algorithm like in more like real life setting. So as I said, cost is relatively low, just one additional mixing proportion per one alternative representation. And one more interesting thing that is, so we already talked with you about the possibility that several components are needed to model a group of data, right? And typically such components overlap considerably, and we based our merging on the overlap between components. But in this interesting application, actually, we can have one class, let's say 0s or 8s. And those representations can be in very different places, and they can have very minimal overlap. Okay, so this is a little bit unusual, basically.
So for 0, for example, you want to read it off of 8 points on the 0. So the machine should see the 8 points and understand that it's 0 instead of 8.
Right, yes. So basically we have k components, but in this case I would prefer to call them like classes maybe. Okay. So 0, 8 or 9. And within each class we have several representations possible. And the goal is that the algorithm goes through all possibilities, alternative representations, and tries all of them and tries to group those representations in such way that they belong to the same class. So basically 0s are going to be grouped with 0s, 8s are going to be grouped with 8s.
You have 8 points that you...
8 points, each point has 2 coordinates,
yes,
x and y, 16.
Data
yes.
points, and machine should recognize 0 or 8 or 9. Or...
Yes, based on these observations. Each observation consists of 16 coordinates.
But if you give me 8 points, I can make 0 out of it, I can make 8 probably out of it. Isn't that possible? I have 8 points on the plane. I can do like this, that could be 8 or 0.
Like for example, if you take like 9, right, let's say, and these are going to be like 8 points here, and you take 0 in these points, you see, it will not be probably easy for you to rearrange the points.
No,
in such a way that
you have 9, you can put 8 points.
Yeah.
But if you start with 8 points, how do you know if it corresponds to 0 or 9, for example? I start with 8 points. Oh, it's not how you do it.
You always start with 8 points, but let's say you have 0.
No, don't throw out the 0. Just put 8 points on the plane.
Okay. So you have something like this: 1, 2, 3, 4, 5, 6. Okay, I have 5, 6, 7, 6, 7, 8.
Okay. So if these points are
basically my claim, of course, if you somehow can rearrange these points and get 9, then we're in trouble, right? Basically, then there will be misclassification. But I don't think you can rearrange these points.
Okay, I got the idea.
Like, you see, this is probably also related to how the data got collected and cleaned. Because, strictly speaking, I don't think you can get something like this and then, I don't know, going back, because these are equally spaced. And
okay, so there's some condition.
Right, so of course, yes, and hypothetically speaking, yes, it's completely possible that your representation styles will in conflict with each other, and then we will get some misclassifications.
Yeah.
And it's definitely possible. But fortunately, digits are not that similar. All right, so now we can talk about clustering metrics and tensor varied data. So this is era of big data. We have large sample sizes. We have many features available for our data. And in addition to that, we also have more complicated data structures. We have higher dimensions. And this is what we're going to talk about today. So the majority of existing clustering methods actually focus on vector data. This is the vast majority of, I would say 99% of clustering methods focus on vector data. But there are actually many situations when we have data in the matrix form. Here I just provide several examples. For example, we observe multivariate data over time, right? So basically we have a vector observed over time. We can have repeated measures, right? So multivariate vector, like we have vector observed, we have repeated measures. We can have two-factor observations, and each factor can have several levels. So basically we have a table. Or we can even have images, right? We have X, we have Y, and we might be interested in clustering images. That's another possibility. So a couple of illustrative examples of where we can observe these things. Also data collected from different sources. So the first data set is collected from the International Movie Database, IMDb. So we have collected 105 comedies between 2014 and 2016. And the way how these comedies are assessed by customers, they assign scores. And this IMDb website presents average scores for each movie. And the data are presented as tables, basically. And there are two factors, gender, males, females, and there are 4 age groups. So literally we have a table 2 by 4. And we have 105 data points. Each movie basically is represented by a 2 by 4 table. Another example, so this data set is obtained from the FBI website. It's publicly available. And it is about crimes in cities, in different cities. And because there are so many cities in the United States, we focused actually only on the cities with population of at least 100,000 people. And we collected the data for the years from 2000 to 2012. And the FBI website reports 7 major crimes. So the first 4 are violent: murder, rape, robbery, and aggravated assault. And 3 property crimes, so motor vehicle theft, burglary, and larceny. If we dropped the cities with some missing records, and as a result we obtained 236 cities, 236 data points, and each data point can be represented as a matrix 7 by 13, because we have 7 crimes observed over 13 years. All right, so now let's take a look at what can be done in terms of finite mixture modeling. My sample now will be Y1 to Yn. I will assume, again, IID case. So I have n p by t dimensional observations. So each, again, observation has t rows and t columns. And I will denote each matrix as capital Y. And one immediate candidate for modeling such data is the so-called matrix normal distribution. There is matrix normal distribution that has the PDF of the following form. Here Y is P by T matrix, M is the mean matrix, also dimensionality is P by T. Sigma is the covariance matrix that is associated with the variability in rows. So it's a P by P covariance matrix. Then psi is a T by T covariance matrix that is supposed to model variability associated with columns. And there is a very important and interesting relationship between matrix normal distribution and multivariate normal distribution. So basically, if we take a matrix and we vectorize it, so we create a, instead of working with P by T matrix, we create a vector of length Pt. If we vectorize it, it actually follows the multivariate normal distribution, but with the covariance matrix of special structure. So it's a Kronecker product of psi and sigma. So in some sense, we can also see this distribution as a partial case of the multivariate normal distribution. But this construction takes into consideration the matrix form, right? That we have rows and we have columns. There is one important matter. There is another non-identifiability issue associated with the Kronecker product. So basically, we can identify the product, but we cannot estimate matrices psi and sigma in a unique way. So we have to introduce an additional constraint. Usually, people introduce this additional constraint on the second matrix, on the matrix psi. One possibility is to say that determinant of psi is going to be equal to 1. Some people, like I think Cinzia and Veroli, used traces, like basically said that trace is equal to a constant. Some people, in particular, like sometimes the people put constraints on the first element in the matrix, but some additional constraint would be needed to make the model identifiable. So in this model actually is not very complicated, and surprisingly, it shows actually very good results in many situations. And this is relatively, I'm not saying this is very new, this is relatively new in finite mixture modeling literature. So the first paper on the use of Gaussian mixture, matrix Gaussian mixture modeling, as you can see, the first papers occurred in 2011, 2012, and primarily by Cinzia from University of Bologna. So this is a good model, very attractive from mathematical point of view, like interpretable. But oftentimes, as we already discussed, normality assumption is in question, right? So if we take a look, for example, at our crime rates, you can see that what we observe for murder rates, for burglary rates, for these cities we selected, it seems like the data shows signs of skewness, right? So we have to deal with skewness somehow. Okay, so what about matrix skewed distributions? So first attempts, according to what I know, first attempts to model skewed distributions were actually taken by Arjun Gupta from Bowling Green. And it was around 1999, the first attempt. Actually, this guy, this is Denis Agdemir, he used to be my classmate in Bowling Green. And Dr. Gupta even published a book, like this is his book, I believe, on matrix varied distributions. So let's, again, this is first attempts to address matrix varied skewed distributions. Then around 2018, 2019, the first attempts to include skewness ideas into matrix mixture modeling have been seen, and I'm actually advocating for the transformation mixture model because it's, in my opinion, this is quite simple idea and not very difficult to implement. So we will talk about this a little bit. We have already seen this idea, right, before, yesterday, just very briefly I mentioned it, but again, the idea is the following. If we have our y, and it follows some distribution, but we don't know it. But we assume that upon some transformation, and the functional form of the transformation is available to us, we assume that we can reach like something like near normality. We can apply back transform and basically get the PDF of the original data. Of course, the success of this idea is subject to finding a suitable transformation, because if we do not reach normality, we may be in trouble. But there is an abundance actually of transformations, and we can try to find an appropriate one. As I mentioned last time, power transformation of box and clocks is not necessarily a good choice, because first of all, it works only for R+ and can accommodate only right skewness, and there is nothing that prevents your data from being left skewed, right? There is an alternative that is better, exponential transformation proposed by Mendley, like 12 years later. And the advantage of this is that it works for R and can accommodate both late and right skew. So this transformation is actually, in practice, it also shows considerably better results than both scores. Okay, both ideas, both transformations have been seen in mixture-related literature. Excuse me. But actually there is an issue with both transformations. If we take a look at the functional form of these transformations, we can see that the transformed variables are going to be bounded by -1 divided by lambda. And this is not a very nice feature because we want to get normally distributed data upon transformation, right? And the data will be bounded. So there are many books and papers that just ignore this situation. And even actually the original paper by Box and Cox employed likelihood inference and just ignored this situation. Some people say that regularization will relax this issue quite effectively. Like, for example, this is what Manley said in his paper in 1976 while he was arguing for his proposed transformation. He was saying that Draper and Cox have pointed out that if the parameter of the power transformation is chosen so as to maximize the likelihood function for samples on the assumption that the transformed data will be normally distributed, then the transformation is likely to regularize the data even if the assumption is not true, basically. Okay, so many people basically choose to ignore this issue, but if you don't want to ignore this issue, there is a better transformation proposed by Yeo and Johnson. This is a power transformation that actually maps R to R, and three of the issues, like it doesn't have a bounded support. So I would recommend this transformation probably. Although Manley transformation also shows quite good results. All right, and again, as I mentioned, various transformations can be employed, and to keep the, I will try to keep the notation general without being specific which transformation we're going to use, but actually most often I will use this one. Okay, now what about multivariate transformations? There is a very common approach. Of course, it has some limitations, but the assumption here is that coordinate-wise transformation can lead to a joint normality. And this idea, again, is well known and documented in literature. There are like hundreds of papers using this idea. And if we assume that this is a reasonable assumption, then we are getting this distribution for the vector y. I have to put small y here because the next slide will have capital Y for the matrix, so I wanted to distinguish them somehow. All right, what happens now with matrices? So if we use the multivariate transformation, if we generalize this multivariate transformation in here to matrices, we can actually take a matrix lambda, which is going to be a matrix of our transformation parameters, and we can apply transformation in a similar fashion, right, with lambda 1, 1, etc. being just elements of the lambda matrix. And then we can assume that this transformation leads us to roughly matrix period normal distribution with parameters m, sigma, and psi. And if this holds, this suggests that we are going to get the following distribution for y. So the same construction. This is Jacobian associated with transformation, and capital phi here, it's PDF of the matrix varied normal. All right, but the problem with this approach is that the interpretation of lambda is not particularly appealing because it seems like every cell in our matrix is going to have its own transformation, right? We will have so many different transformations. And in addition to that, this matrix can be quite big, and the analytical solution for lambda is not going to be available, so we will need to estimate lambda numerically. So there is an alternative parameterization, which is more appealing, not necessarily better working, but more appealing from the interpretation point of view and from, of course, estimation point of view. What if we say that lambda is equal to this? So basically, we introduce two vectors, lambda and nu, lambda is going to have skewness parameters associated with the rows, and nu is going to have skewness parameters associated with the columns. And then for each cell, you can get skewness parameter as a sum of skewness parameter in a particular row and skewness parameter in a particular column. So this additive, basically additive parameterization for the skewness parameter. Makes sense, right? So this is how we can parameterize this matrix then. So of course we reduce the number of parameters quite considerably, but again there is a non-identifiability issue because we can, like that follows from here, and we need to introduce an additional constraint on, we have chosen the second vector to put an additional constraint on. Actually it's very easy to see why we have non-identifiability issue. Imagine that I will shrink this matrix just to one column. I will have like p skewness parameters associated with the rows and still have one skewness parameters associated with the column. But clearly I don't need this extra parameter associated with the column, right? So I need to drop it. And one possibility is just to say, to apply the restriction that nu t is going to be equal to 0. So basically skewness associated with the last column is equal to 0. Actually, it has, I think, somewhat attractive interpretation, because then lambda is our baseline skewness associated with the rows for the last column. Okay, because lambda nu t is going to be 0. So this is the row skewness for the rows associated with the rows for the last column. And then each additional nu1, nu2, up to nu t minus 1, it's an adjustment for the particular column. Does this make sense? All right. So, okay, here is the EM algorithm. Everything is pretty much as always. We have again the stereo probabilities. We have mixing proportions. Skewness parameters need to be estimated numerically. Interesting thing about mk, sigma k, and psi k, everything is on the transformed variable scale. So actually the calculation of these three is almost the same as for the Gaussian matrix mixture model. It's just for the transformed variable. So it's very actually simple and not very difficult to implement. Here I had some small simulation example. So we simulated the data from this matrix transformation mixture model, tried different sample sizes, 100, 500, 1000, tried different overlap. Now we know what the overlap is, right? So it controls the complexity. So this is the easier case, this is the more difficult case. 5 varied matrices are 5 by 5, and the mixture has 5 components. So you can see the results here. There are several interesting things I just wanted to show you. Of course, first of all, B. B stands for how many times a particular model has chosen the best solution according to BIC. So if it's 498 versus 2, it means that in 498 cases out of 500, MTM, this transformation mixture, picked the best BIC, and Gaussian mixture picked it 2 times. So, but again, this is like totally expected because the simulated, right? So these are median BIC, median adjusted random index, and you can see that with the increase of the sample size, of course, we have an improvement in terms of the adjusted random index here, and especially here, right? One interesting thing is S3, S4, S5, S6, S7. These are the numbers of spurious solutions we obtained for each situation. You can actually see that if we have a very small, it's somewhat related to what you asked, I think, yesterday. If we have a very small sample size and our model is pretty complicated, it is actually quite likely that we will produce those spurious solutions where we basically pick some random pattern and try to construct a component on the random pattern rather than trying to capture the systematic structure. Yes.
Sorry, the difference between MGM and TM is what here? It's
MGM is matrix varied Gaussian,
Yeah.
and MTM is matrix varied transformation. So basically, MTM can accommodate skewness. In all these cases, it should do better because we simulated from MTM and clearly, right? So it's like MGM is a partial case of MTM. All right, so this is the case now of a little bit different. Here we simulate these mixtures actually from the Gaussian, matrix Gaussian model to be fair, right? And to see what happens. Actually, as we expected, BIC now picks the other model, right? Because we simulated from it. We don't need that many parameters as MTM actually has. And but if you take a look at the adjusted rand index, you can see that our values are quite competitive, like they're actually quite similar. So again, in this particular case, over-parameterization is not necessarily the problem. It's more important to fit the data well. I'm not saying it's always like that, but oftentimes, if your model is not extremely over-parameterized, it's better to have some extra flexibility, at least if your goal is to do model-based clustering. Because oftentimes, as we talked right before, you just don't know which model to choose. It's better to choose more flexible model so that you can accommodate data nuances, like everything. All right. All right. So again, the thing is that skewness parameters are not always needed, right? Because currently I'm doing either I'm employing Gaussian matrix mixture model with absolutely no skewness parameter involved, or I use many skewness parameters, right? I have actually P plus T minus 1 and times K skewness parameters, and it can be actually a pretty high number. So it would be a good idea to try to remove these unnecessary skewness parameters for the following reasons. First of all, it's going to be better for the model if we get rid of the unnecessary parameters. Second, it's actually another interesting aspect. It can be useful for diagnostics. You can take a look at which variables actually present skewness, have skewness, and where in which variables you have no skewness. So for diagnostic purposes, it might be also of interest. So again, we can do backward selection. So start with all skewness parameters included and start dropping them one by one. Forward selection, or we can use some other methods. And here is an illustration. So this is Gaussian, this is transformation, this is transformation forward selection, transformation backward selection. Again, how many times a particular model produced the best BIC. So you can see that only these two models compete with each other, basically. Okay, what we have simulated, it was a 3-component mixture model, 4x4 matrices, again, 2 different levels of overlap, but in each component I had only 2 lambdas and 2 mu's not equal to 0, right? If you take a look at what happens when we increase the sample size, so this is, okay, let me show you. This is basically how many lambdas, okay? This is MTM, this is how many lambdas and how many mu's are included in the models. Of course, in the Gaussian, we do not include any skewness parameters. And this is how many these methods include. And this is how many lambdas are correctly included in the model on average. This is how many lambdas are incorrectly excluded from the model on average. Okay? So basically, we want these to be smaller, we want these to be closer to actually 6 in both cases, because we have 2 lambdas and 2 mu's and 3 components. So and you can quite easily see, I think, that if we increase the sample size, we actually get closer to 6, 0, 6, 0, 6, 0, 6, 0. So with the increase of the sample size, we are getting much better. And adjusted rand indices a good one. All right. Now let's take a look at our data sets. So the first data set was IMDb. This was the data set with the movies. I considered 8 different models here. So Gaussian, transformation with forward selection, backward selection, and this little A stands for additive structure for the mean matrix. Okay, this is what I actually didn't mention. That for the mean matrix, we can also use the similar idea. We can take matrix as is, matrix M, or we can parameterize it in a similar way with skewness, right? So we can say there are some parameters associated with the rows and there are some parameters associated with the columns, and basically each mean element can be modeled as the sum of the two. Okay, so different things, and this is the best solution that we found. Here, this is cluster 1, cluster 2, cluster 3. These are female ratings, these are male ratings. And these are the 4 groups, age groups. So these vertical lines represent 4 age groups. So if you take a look at, if you consider, okay, what's the difference between clusters 1, 2, and 3? It seems like this cluster includes higher ranked movies, right? And cluster 3 includes pretty much, especially for males, right? For males with movies that are apparently not liked much. And these are some mediocre movies. It's actually interesting if you take a look that apparently some movies are quite liked by females and sort of pretty much hated by males. Overall, I think actually that if you take a look, that these ratings, right, they're higher actually than here and everywhere. So I think like females are probably kinder, okay, somewhat in the assessment of movies at least. And if you take a look also, it's interesting, we have this shape, like U shape, right? So it seems like people after 44 and before 18, they're also sort of on the more leaning to give higher scores. And I guess the most critical group is people from 30 to 44. But okay, if you know these comedies, this is basically, this was the clusters produced. I don't know. To be honest, I didn't watch any of these movies, but you can take a look and say, are they like bad movies or like? They were supposed to be pretty bad, so based on the rating.
It's like they're so bad, they're good.
I actually I need to go back to the data and see which movie was this one that apparently females liked so much, and also probably this one. Not sure. Okay. All right. So now. Do you remember, like I showed you this slide yesterday, this was basically about how different parsimonious models can be implemented in the Gaussian mixture model, right? So we can focus on different, same or different volumes, shapes, and orientations of Gaussian components. And if we want to use this parsimonious models idea for matrices, we can actually do it quite easily as well. So there are 14 different parameterizations, and we will have 14 different parameterizations for sigma, but we have an identifiability constraint, right, for our matrix period normal. So because of this, if we incorporate this constraint, we will not have 14 constraints, so basically volume will be exactly the same, and it leads to 7 parameterizations for psi k. So overall, we have 14 parameterizations for sigma k, 7 parameterizations for psi k, so we have 98 in total. And if you, as I mentioned, like there is general and additive parameterization for the matrices. Even if we do not touch skewness at all, just for matrix varied Gaussian distributions, we can actually produce 196 different models and try to choose which one is the best. So this is basically an extension of what MClass does. MClass is the package for matrix for Gaussian Mission models. And this is basically a table how it looks like. So all different models. So the first character represents the mean, additive or general parameterization. Then the 3 characters here represents the sigma structure, and the last 2 characters represent the psi matrix structure. And just to show you that it's possible to run and estimate, actually, this is for the NDB dataset. Everything is like we calculated it can be done. And here. This is for the transformation mixture with different unit parameters. And this is the summary of the obtained clustering results. So basically here we can see that we have several solutions. Solution A, B, C, D, E. These are model names. This is the rank of the model based on BIC. So this is the best BIC, second best BIC, etc. If we take a look at the clustering solutions and try to compare them, this is basically what we can do. This is solution A, solution B, so it's like pairwise comparison. Solution like color represents the cluster, and solution we have lines that go horizontally and lines that go vertically, like as you can see, like this, right? Do you see there is a mismatch? Like there is a pink color here and then magenta here. It means that there is disagreement between these two classifications. If we would have exactly the same color everywhere, it would mean that 2 partitions match perfectly. It's just a visualization tool. Okay, so what can we see? There is no problem between this khaki and magenta clusters, right? There are no misclassifications. We can see that if something goes on, then solutions are different because some movies from the first cluster fall into the second, or vice versa, right? You see there is some pink here and here, etc., or a little bit more here, but it's just a matter of probably several movies, not too many, you can see. Okay.
3 minutes.
Okay.
You started a little late, so.
Okay, thank you. So now we can get to our second example. Actually, everything like we can do the same approach with crime dataset, right? There is no problem with that. The only concern, at least slight concern, is that if you think about our matrix psi, it's actually, I think it has 13, right? It's 13 by 13. And potentially, if we think about modeling time, we can have actually huge matrices, right? We can observe some information over 100 days or over like 50 years, right? So we can have actually many time points. So somehow it would be nice to, instead of assuming some general form of the covariance matrix, or even those parsimonious forms that we considered, maybe we assume some time series related parameterization of covariance matrices. So one possibility is, like this is the simplest basically model, just autoregressive order 1 model. Here's the covariance matrix of this form. So this pretty much the correlation matrix, and it has 2 parameters, just correlation and the variance associated with R1. So we can try to employ this. I will actually, I can motivate why this model is good. I can show you the autocorrelation structure, and basically actually it fits extremely well for this crime data set. It works very well, this one. But another advantage of this model is that it's very convenient, again, mathematically, just because of the structure. Even we need to take determinant, right? We need to calculate the inverse. Actually, we don't need to invert it. We can very easily calculate the analytical form for the inverse, and this is very convenient because instead of inverting matrix that is maybe potentially 100 by 100, we can do it in milliseconds, right? So this is basically the way how we can do it.
Just 2 minutes.
2 minutes, okay. All right. So here, if we take a look at my crime example, actually the matrix M, the mean matrix, can also have many parameters, right? And we can probably employ the idea with regression here, as we already did. We've seen how to use regression before, so we can probably employ something like this for matrices as well. So if we introduce, this is basically going to be a matrix of my explanatory variables, and here I will employ only time, right? So I will use the first column for the intercept, basically once, then time, maybe time squared. I don't know which polynomial function I'm going to use, so I will choose it. And beta k is going to be a q by p matrix of coefficients. And so basically we hope that this beta will have much fewer parameters than the original matrix M. So then we can write the matrix regression this way. And one more thing before we probably interrupt, okay? If we think about what our columns represent, they are all associated with time. And if we think about the interpretation, from the interpretation point of view at least, it would be nice to have exactly the same transformation parameter for each time point. Probably we're not very much interested in transforming every time point in a different way, at least from the interpretation point of view. Then it would imply that nu1 is equal to nu2 is equal to nu-t, right? All of them are the same. We just don't have a common parameter. But because we have a constraint, because of the non-identifiability, the last parameter is equal to 0, meaning that all of them are 0. So we actually can completely ignore the skewness associated with the columns, and we will have only vector of skewness parameters associated with the rows of the matrix. Make sense?